Today we are diving into something called pharmacodynamics, which, in simple terms, is the science of what a drug actually does to your body once it's in there. I mean, really think about it for a second. How can one little aspirin get rid of a pounding headache? Or how does a single antibiotic capsule start fighting off a massive infection? It's not magic, not at all. It's actually a super precise biological mission. Let's break down how it all works. Okay, so first things first, let's clear up a really common point of confusion. You've probably heard the term pharmacokinetics. That's all about how your body absorbs, moves, breaks down, and gets rid of a drug. It's what the body does to the drug. But what we're talking about today is its partner, pharmacodynamics. That's the flip side of the coin, what the drug does to the body.
So, if you want the official, textbook definition, pharmacodynamics is the study of a drug's effects and, crucially, its mechanism of action. It's really the story of how a chemical substance starts a conversation with a living system.
So how does a drug even know where to go and what to do? Well, it all starts with a very specific mission. Find the target.
Yeah, a drug isn't just a grenade that you toss into your system hoping it blows up in the right place. No way. It's way more sophisticated. Think of it like a guided missile, engineered to seek out and interact with very specific molecules, which are usually proteins, to get the job done. This incredible precision is what makes modern medicine so powerful. And these guided missiles, they're usually headed for one of four main destinations. They can target enzymes to kickstart or shut down chemical reactions. They might interact with membrane carriers, which are like the bouncers that move stuff in and out of your cells. They can also open or close ion channels, controlling all the electrical signals. And, probably the most common target of all, they bind to receptors right on a cell's surface. All right, so the drug has found its target. Mission accomplished, right? Well, not yet. Now it's time for the action plan. You know, when you really boil it all down, most drugs do one of two things. They either turn a natural process on by mimicking or boosting a signal your body already uses, or they turn a natural process off by blocking it. It's basically a high-stakes game of biological red light, green light. And here are the two star players in that game. You have the agonist, that's your accelerator. It binds to a receptor and fires it up, triggering a response. Think about how morphine activates opioid receptors to kill pain. Then you have the antagonist. That's the brake. It binds to the same receptor, but it just sits there. It doesn't activate it, and it physically blocks the body's natural activators from getting in. A great example is beta blockers for high blood pressure. The classic lock and key analogy is absolutely perfect here. The receptor is the lock. An agonist is the right key. It fits, it turns, and it opens the door. An antagonist, on the other hand, is a key that fits in the lock but won't turn. And now it's just stuck there, so the correct key can't even get in to do its job. So one activates, the other blocks. Simple as that. But of course, all this targeting and action has to be controlled really, really carefully. Too little of an effect is totally useless, but too much can be downright dangerous. It's an incredibly delicate balancing act. And this leads us to the therapeutic window. Honestly, one of the most important concepts in all of medicine. It's the sweet spot, the dosage range where a drug is effective but isn't causing a bunch of nasty side effects yet. Some drugs have a really narrow therapeutic window, which means the line between helpful and harmful is razor thin. And those are the ones that need to be monitored very, very closely. And this chart makes it super clear. Down at the bottom, you've got an ineffective dose, not enough to do anything. Way up at the top, you've got a toxic dose where the side effects are just too much. But that zone right in the middle, that's our goal. That's the therapeutic dose. So a drug's effect isn't forever, right? It has a life cycle, which brings us to the next big question. How long does the action actually last? This is called the duration of action, and it's pretty much what it sounds like, how long a drug keeps producing its desired effect. This depends on a ton of different factors, like how quickly your body breaks down and clears the drug, and hey, that's pharmacokinetics coming back into the picture. See how they're connected? We can actually break this whole life cycle down into phases. First, there's the onset. That's when you first start to feel something. Then the come up, as the effect gets stronger. Then you hit the peak, its maximum intensity. After that is the offset, when it starts to fade away. And finally, you might have some after effects, which are just those lingering feelings after the main event is over. So, to wrap it all up in a neat little bow, pharmacodynamics is the story of what a drug does in your body. And that story is told in three main parts: its target,
its action, and its effect over time.
So the next time you take a pill for a headache or anything else, just take a second to think about the incredible journey it's about to go on. A tiny guided missile seeking its target, all set to perform a complex and really elegant dance inside of you. Thanks for tuning in.